So in order to use linear programming, there are a couple things that are requirements. So first we have to make sure that we're trying to maximize or minimize some objective function. So this is some quantity. It has to be expressed as a linear equation. And again, a lot of times it's either like maximize revenue or maximize profit, or it might be minimizing cost or minimizing time, for example. We also have to have restrictions. These are the constraints. So these are the things that are stopping us from doing better. A lot of times I like to think of this as what types of resources do we have and what is it that is limiting us from utilizing those resources. So is it time? Is it money? Is it hours, labor hours, machine hours, things like that. And then there must be alternative courses of action to choose from. That one's a bit broad. That's actually true no matter what kind of model we put together. We don't need a model if we don't have different things that must be chosen from the different alternatives. And then everything has to be expressed, the objective and the constraints, in linear equations. Then the components of an LP, three big components. There are the decision variables, the objective function, and then finally the constraints. So the decision variables I like to think of as the outcome. So if I'm having trouble trying to figure out what the decision variables should be, I often think about, well, what do I want the output or the outcome to look like? What is it I have to hand off to the decision maker so that they can make a decision? What is the recommended course of action? So those are my decision variables. The objective function then is a maximization or minimization of a linear function of some of those decision variables. It might be all of them, it might be some of them. Sometimes it's none of them, it's auxiliary variables, but in our case that's very rare. And then there are constraints. These are the restrictions on our resources such as time, money, labor, etc. And those again have to be also linear. So there are four big assumptions to linear programming, and the first two come directly from being linear. So first is proportionality. So I've written here the contribution of each decision variable is proportional to the value of that decision variable. So I want you to take a minute, or a second or two, to think about how you would translate that for your third grade nephew. So could you do it? Could you actually translate that for someone into something more simple so they could understand it? Hopefully you could. So here's how I would probably explain it to my third grader. Right? I would say, all right, I'm selling rocks. I'm just going to sell each rock for $1. So if I sell one rock, how much money do I get? $1. If I sell two rocks, how much money do I get? $2. If I sell five, I get $5. That's proportionality. In essence, it's the slope of the line. Right? So it goes up in proportion to how much I sell or make. Then we have additivity. That's the contribution of any variable is independent of the values of other decision variables. So this is in the case of selling something. I'm selling more than one product. So now I'm selling rocks and sticks. Right? Rocks are $1. Sticks are harder to come by, so they're $2. So then if I sell one of each, I can add up the $1 and the $2 for a total of $3. So it means we can put plus signs and minus signs in between the different variables. The third assumption is divisibility. This means we can have fractions, decimals. So that means now I can sell 1.27 rocks and 3.19 sticks. Right? So in some situations, that's okay. I can have fractions and fractions mean something. In other cases, it may not mean something. If that's the case, then we would want to enforce integers, whole numbers. We are going to do that in our next unit, integer programming. For now, we're going to assume that fractions are okay. And then finally, we have certainty as the fourth assumption. Here that means all of the coefficients, that's the numbers that go in front of a variable, are known with certainty. That means we are dealing with a deterministic world. That means that a number is a number. So when I say $2 for a stick, that means that it's $2 always. I don't change it. I don't get price discounts. It's not a random variable with a mean of 2 and a standard deviation of 0.15. No, it is a 2 and only a 2. So the thing is, if we don't like this assumption, there is another alternative called stochastic programming. It's much more difficult, but some people find it more useful. The other thing we can do for this one, and this is what we will do in this class, is that we will look at sensitivity reports and do a sensitivity analysis around some of those coefficients. So what happens if the $2 is off, right? So we can look at how robust the solution is, the recommended course of action, looking at the sensitivity report. So we'll get to that when we get to sensitivity reports.